Michael. Can you hear me? I can't hear you. Anyway, welcome to Astronomy Club of Tulsa. My name is John Land. I'm the president this year. This lovely lady over here in the red was the past president. Miss Ann, we're glad to have her. And Miss Tamara's here somewhere. She's our last year's president. So that's good that we have some people. How many guests do we have? All right. I've got two down here in the front and two back there. And I don't see the other one, but somebody's pointing over there for me. So anyway, we're going to have a good program tonight. Our best guest speaker, Michael Hann, is going to tell us about building a radio telescope here. So anyway, so we hope you all enjoy the meeting and learn a little bit and be able to join with us. When we finish, I'm using my phone right now so the people on the Zoom can see us. But when we finish, I'd like to kind of get everybody in one area so I can take a picture or so publicize our website a little bit better. So welcome to our December 10th Astronomy Club of Tulsa meeting. You can leave lights up a little bit, Dan. So go to the next slide. Here's some of the things we're going to do tonight. We're going to talk about our observing nights. We're going to talk about a special one that's taking place not tomorrow, but the following Saturday at Gathering Place. Talk a little bit about the Geminid meteor shower that's going on right now this weekend. Show you a few little slides of the lunar eclipse that we had a couple of weeks ago. How many got to see that? Get up and freeze yourself in cold to see the lunar eclipse? I see Maria's hand over there. Oh dear, I got a phone call coming in. Anyway, the comet. Anybody else seen the comet? I saw a few pictures on our club Facebook page that people took some pictures. Some things about looking forward to 2022. And then we'll introduce our guest speaker. So do that one for us. Here's our events. I don't know how to get rid of this. Hang on a minute. Get rid of itself. Due to the early sunsets during central starlight time, is what I like to call it. But the sun goes down, as you know, it's already getting dark well dark by 6 o'clock, which makes it real difficult for people to get off work, get down to the observatory, get the thing open. And so during the winter months, we're going to have observing nights on Saturdays and not Fridays. So that's what we're going to be doing. Unfortunately, the third quarter moon and the new moon land on Christmas weekend and New Year's weekend. So we're not even going to try to have one Friday or Saturday Christmas Eve and Christmas Day. But if there's enough interest, we'll try to be open on January 1st if you want to skip the football game. So my grandson's all excited. He's a Baylor fan, and they're playing Mississippi State or somebody like that. But anyway, so that's coming up. Our members only night, we're going to have that on January 1st if we get enough interest, and I'll send out an email about that. Our next meeting here is going to be January the 7th, so you'll want to plan on that. And it's open to guests too. Sometimes I get people on the web say, can a guest come, or how much does it cost? No, everybody can come to our Jinx meetings. We're going to have an observatory night on the 22nd of January, which is close to third quarter. And that one will be open to guests, but we're going to ask them to RSVP so we'll know how many are coming. But the members can come, you don't have to RSVP, of course. And then January has 2 new moons. So we have another one on January 29th. So we're gonna have 2 members' nights, and hopefully in the middle of that, a night where guests can come. And we'll see how that all works. Of course, all of that depends on how things go with this COVID mess that's going on. All right, next one there. This is the one I was telling you about. We're going to have a opportunity to set up our telescopes. We got 11 volunteers. Going to set up telescopes at the gathering place. We've been invited. They're having a couple of weeks long, what's called Winter Wonderland event from the 17th to the 26th. And they've asked us to set up some telescopes to see the planets and the moon. And I don't know how well you can see that map, but if you've been to the gathering place, if you go in around where the normal visiting entry place and follow that road around, there's a parking place there where you can walk into the lower level of the boathouse. We're going to be on the hill above the boathouse, so you can hopefully find a parking place a lot closer and then have to walk all the way through. But you may want to walk through because they're going to have their Christmas lights. It's certainly not going to be a dark sky sight, but the hill has a nice view over the river. And of course, all the planets are in the south, southwest, so they'll be good to see. And there's a possibility, I'll show you a chart, we might be able to see that comet. It's going to be underneath Venus that night. I don't know how long the horizon will be, but we might be able to make it out in a telescope. So anyway, that's what's coming up the 18th, weather permitting, of course. So there's information on the website about it. All right, next one. Our Gemini meteor shower peaks this weekend. Technically, the peak of the shower is right after midnight on Tuesday morning. Sky and Telescope says about 1 a.m. on Tuesday morning. But looking at the weather report, it's probably better to try the next 2 or 3 nights. There's 2 factors. One, it's supposed to be clear. And 2, each night the moon stays up longer. We've got a nice bright gibbous moon, sets at midnight tonight, 1 a.m. on Sunday night, 2 a.m. on Monday night, and 3 a.m. on the day of the 14th. So you could avoid the moon a little bit. And the meteor shower goes on for several days. Just the peak activity is predicted sometime in the evening of the 13th and 14th. Gemini passes overhead about 2 a.m. this time of year. So from midnight to 4 until you freeze to death, that'd be the time. It's kind of unusual. Most all our meteor showers come from comets. And we're familiar with seeing a comet and the tail coming out behind it. Sometimes they stretch out more than 1 million miles. And those little particles of dust and such continue in orbit, and Earth comes through there and captures some of them each time we go through that part of space. But this one is from an asteroid, 3200 Python, if I can pronounce it right, Python. It goes around every 1.4 years, and as it does, little bits of it flake off and form meteors. We visited a few asteroids, and if you've seen pictures of them, they've got all this rubble on their surface, and a couple of them seem to be nothing more than a big rubble pile. Think of a big gravel pile going around in space, little bits of stuff that kind of stuck together but never did quite melt internally. This one's kind of slow for meteor showers. It's only 80,000 miles an hour. Some of them are 3 times that much. So anyway, it's a Gemini shower. It's one of the 2 best of the year. Not observed as well because of the cold temperatures. That's coming up this weekend, so if you want to brave being out in the morning or the next couple of mornings, you might be able to see a few. All right. The lunar eclipse that we just had. There's some pictures. I had these in the newsletter, but some of you probably haven't been there. Up at Skip. Where's Dr. Skip here tonight?
I haven't seen him.
I haven't seen him, but Skip Whitehurst, one of our board members, took a time-lapse images of the moon. I was visiting with him when he was setting this all up at our last observing night. He wrote a little program to focus his telescope not on the moon, but on the Earth's shadow. Earth's shadow is called the umbra. So he calculated the point in the sky that was directly opposite of the sun and took a whole bunch of time-lapse photos on that part of the sky. You could see the moon going through it. So the umbra is the dark inner phase of the eclipse. I used to teach astronomy, and that's one of the things we did. The ancient Greeks knew the Earth was round. And one of their proofs was that anytime you had a lunar eclipse, the shadows that went across the moon, which they figured out why that happened, the shadows that went across the moon was always curved. It didn't matter what time of year it was. So the object that was casting the shadow had to be a sphere. One at the bottom is some excellent photos that Brian Wattenbarger, I guess it's how you pronounce his name, one of our members, took with his telescope camera. And the wide field one I just took with my iPhone. I've got a little app called Nightcap that takes a whole bunch of little short exposures and stacks them together automatically. So up in the upper corner, you can see Pleiades above the moon. The moon was in Taurus, and you can see Orion and some other things there. So that was kind of nice. I was pleased with that. All right, next one. We have a nice comet out there. For those of you brave enough to do it, it's been in the morning sky. It's a one-time thing. It was discovered on January 1st, 2021. It was the first comet discovered this year. That's what the A1 means, the first one of the year. And it will pass closest to the sun at the end of this month. But it's been in the morning sky. It's been, came past in my images there. That was the morning of the 3rd, and it passed right near the globular cluster M3, which made it easy to find. The first morning on the 2nd, I couldn't really see it in my binoculars. I could sort of know if I knew where it was and looked carefully, I could make it out. The second morning was a little easier to see. I've got some 15 by 80 binoculars, but it's been diving quickly toward the horizon, so it's pretty much out of view in the morning sky. But as you can see, by midweek next week, it's going to start emerging in the evening sky, but you'll need a good view to the southwest. That's only 10 degrees above the horizon, and that's 45 minutes after sunset. So it's kind of marginal for us to see it. But you notice on the night of the 18th, when we have our thing at the gathering place, some of the guys with our electronic scopes might be able to pick it up. But it's going to be a pretty good southern hemisphere object. And according to what I read, it's up to about 5th magnitude now. It's not something going to knock your socks off, but it's bright enough you could find it with a telescope or maybe binoculars. So that's Comet Leonard. And it's on hyperbolic orbit, meaning that it's coming in and it's not coming back. Its eccentricity is greater than 1, so it's been speeded up on its way. It's going to be thrown out of the solar system. All right, next one. Okay, we're getting ready to celebrate our club's 85th anniversary. Our club, according to our information, was formed in the summer of 1937. So we wanted to come up with some ideas about how to do that properly, and I really need ideas. So if you want to email me or contact one of our board members, just to write up some ideas how we can have some special events and celebrate our club's 85th anniversary. Not too many clubs have been around that long, maybe some of them on the East Coast, but for a Midwestern club, that's pretty amazing. So we need to give you all more opportunities to volunteer. One place we really need volunteers is our observing nights. We need people who will volunteer to come help open up and get things ready for our guests, set up some telescopes on the ground, just welcome our guests, help close up. So we need some more observing night hosting. Don could use some help up running the big dome and the telescope in the dome. You do the newsletter, and I'm always appreciative of people like Michael and Brad and others that give us some articles from time to time. I like to put in some humorous things, some cartoons, some jokes that you might want to create, as long as it has something to do with astronomy. Maybe something that you enjoyed vacation this summer. You visited something associated with astronomy, or you've got a new astronomy toy for Christmas this Christmas. So, speaking of that, before I forget, our friend over here, Brian, want me to tell, or you want to come up and tell him? Yeah. He has something he's going to put up for sale that might be beneficial to some of you.
Thank you, John. My name is Byron Lavity. For the attendees here and those that are watching afar on their computers, I'm getting ready to build a roll-off roof observatory in the backyard because after my accident, bones and everything hurt too much to set this thing up and tear it down all the time. So it's going to be permanently mounted. I have a JMI scope buggy with a 10-inch pneumatic tires on it, and it's less than 2 years old for the condition, and I'm willing to let it go for $500. And if I don't get any takers in the next month or so, I'll put it up on cloudy nights, and there's somebody there who'll snag it. So that's it. Thanks for your time, John.
What that is a cart that has 3 wheels on it, a place to put your tripod, big wheels that you can roll on your lawn, and move your scope around a little easier without having to lift everything. We've got some public events coming up in 2022. We've been invited to come to Oxley Nature Center in January. Got another one I haven't answered yet from Hicks Park. That one's in January. Oxley's in March. And then we have a group coming out to Post Oak Lodge in May. And so we get some opportunities like that. Hopefully, if everything with the pandemic kind of begins to pan out, we want to start doing some, like we did sidewalk astronomy on Saturday evenings, where we just go to a place that has a lot of people. We've been going to Bass Pro, but that's not a very good place anymore from all the trees and stuff. So we're looking for places where we can go that people come by, they stop and look at the first quarter moon, look at whatever planets are out, visit it with us a little bit. So we're hoping to start some of those. There's been some people talk about forming some special interest groups, maybe for astrophotography or something like that. We're looking at updating our club website. So it originally got started in the late 90s when we still had dial-up modems. Only the people with golden hair and gray hair probably even know what that is, but so parts of our website are pretty much out of date. And the coding that we have on our website right now is pretty archaic. So we need to talk about updating it. Some of you younger people, we need to get a better social presence. Got a Facebook page, but I don't know all these other things, instant this and instant that. So are you interested in volunteering to be with the group to work on that? Let us know, okay? Get involved, get some things going for our club. So, all right, anybody else got something to add before we do our guest speaker? All right, our guest speaker for tonight is Michael Hann. I have to work on his name. And he's going to tell us about this wonderful radio telescope that he built. I'll let him tell us. Just a minute, Michael. I got to get rid of this message on my phone. All right.
Hello, I'm Michael Hann. I'm going to talk to you tonight about radio astronomy and also finally about a radio telescope that I made. So the radio spectrum, the electromagnetic spectrum, is a unified phenomenon. We speak of radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, as if they were different things, but it's a unified phenomenon. It's the same thing. They're all electromagnetic radiation. Electromagnetic radiation can be viewed as either waves or as particle, that is, as photons, their equivalent views. Originally, it was thought that only stars would emit observable waves, and that these would be in the visible spectrum. Later, we found that not to be true, that there's also radio wave, X-ray, and gamma ray radiation. Michael Faraday did some early work on electromagnetic phenomenon beginning in 1832. Electromagnetic theory was analyzed theoretically by James Clerk Maxwell, and he published his findings in 1865. Heinrich Hertz conducted spark gap experiments in 1886 to 1889, demonstrating transmission of radio waves. Guglielmo Marconi, about 1896, developed a practical spark gap transmitter and receivers for ship-to-shore radio transmissions. And Max Planck, working on black body radiation in 1900, first published his studies, including his postulate that electromagnetic energy could be emitted only in quantized form. That is, the energy could only be a multiple of an elementary unit. This is kind of some fundamental background for radio technology that is related to radio astronomy. In radio astronomy, there's several forms of radiation sources that are of particular interest. I've mentioned black body radiation. This is actually associated with the heat of objects. In black body radiation of any particular object will have an amplitude across a variety of frequencies. It's broad spectrum radiation, but it has a peak at a particular frequency that's related to its temperature. A hotter object would have a peak at a higher frequency, and so we can actually infer the temperature of an object by observing the peak of this black body radiation curve. Spectral line radiation is associated with transitions of electrons between predefined and quantized energy levels of an atomic nucleus. As a key example, hydrogen clouds close to powerful stars may become ionized by those stars, and as the electrons recombine with the hydrogen nuclei, that is, they fall down in energy levels, they emit photons at a characteristic frequency. One particularly common recombination is at 656.3 nanometer wavelength, which we see as a pinkish magenta color. Emission of light in this way, that is falling from a higher energy level to a lower energy level and emitting light or radio waves, is called fluorescence. Hydrogen clouds that are ionized by nearby stars that fluoresce in this way are sometimes called H2 regions and are often present in areas of star formation. The Great Orion Nebula, M42, is an example of this. The backgrounds of my slides is another example of that. You should be able to see the kind of reddish magenta color there. So that's a spectral line emission that is at a very narrow frequency. Another example of line emission is neutral hydrogen, or H1. It also produces a spectral line radiation, in this case not in the optical wavelength, but in the radio wavelength at 1420 megahertz. It's a very important emission for radio astronomy. Also interstellar molecules such as carbon monoxide and hydroxyls have been observed and are important in radio astronomy. Bremsstrahlung radiation is caused by slowing charged particles and is a broad spectrum sort of radiation. This can happen when a charged particle encounters a solid object and interacts with the atomic nuclei, that is the protons within the atom that it's colliding with. Synchrotron radiation is produced by, causes radial acceleration of charged particles, and this leads to the synchrotron radiation. It's called synchrotron radiation because it was first observed in synchrotron apparatuses. So our atmosphere interacts with electromagnetic radiation that's inbound towards Earth. Much of it is blocked by the atmosphere, but there are a couple of windows. An optical window that's about 1 octave of frequencies wide, and a radio window which is about 10 octaves wide. So optical and radio radiation freely comes in, and we can observe that easily from Earth. Okay, Carl Jansky discovered radio waves from space in 1933. Jansky was born in Oklahoma Territory in October 1905, and his father was dean of the College of Engineering at OU. Later, Jansky was working at Bell Labs in Hamilton, New Jersey, investigating sources of radio interference in the transatlantic wireless link that Bell Labs was working on. He eliminated some sources of this interference, local thunderstorms, far distant thunderstorms, but there remained a hiss that he couldn't identify a source for. This hiss repeated periodically at an interval, he found, of 23 hours and 56 minutes. Well, this is not the solar day. The solar day is 24 hours. The 23-hour, 56-minute interval is associated with the sidereal day. The rotation of the Earth on its axis brings stars back to the zenith on a periodic interval of 23 hours and 56 minutes. From this, Jansky concluded that the radio waves he was observing, that hiss, must have come from celestial sources, from the fixed stars. And ultimately, he decided that this was located in the center of the galaxy. So, optical astronomy could arguably be said to have originated about when Galileo turned his telescope on the moon in November of 1609, or when he turned his telescope on Jupiter in January of 1610, and that was 320 years before Carl Jansky discovered radio waves from space. This was Jansky's telescope. It was an array of dipole antennas that was about 100 feet wide and 12 feet tall. He mounted it on tires and rotated it on a carousel to aimed the telescope at different parts of the sky. Here's a picture of Jansky having plotted his observations against a star chart. Reber was the first radio astronomer that you might call a radio astronomer. He was born and raised in the Wheaton suburb of Chicago, graduated from college with a BSEE degree from what's now the Illinois Institute of Technology, and he was an amateur radio operator. Reber had read Jansky's published papers on radio waves from space and wanted to follow up on this. From 1937 to 1947, Reber was the world's only operating radio astronomer and basically laid the foundations for the science of radio astronomy. He did this while working during the day as a radio receiver engineer to make a paycheck, and at night conducted radio astronomy observations from his backyard at home using a parabolic dish antenna that he had built. He did this at night because there was a problem with automobiles at that time, and perhaps today too, where it generates sparks, particularly the ignition system, opening and closing of points in the distributor, and that creates static that interferes with the telescope. So he waited until after midnight to start his observations. Reber's work promoted or prompted an explosion of radio astronomy after World War II, and this was also prompted by the rapid advancement of radio and radar technology during World War II. And there was an interesting note of trivia. Edwin Hubble also grew up and attended school in Wheaton, Illinois. Reber's mother was a grade school teacher who taught Hubble and passed on a book on astronomy that was given to her by Hubble to Grote, her son, at a young age, which initiated Reber's interest in astronomy. Reber made the first maps of the radio sky surveys, in different radio frequency bands. He identified strong radio sources of Cygnus A, a radio galaxy or quasar, and Cassiopeia A, a supernova remnant. In talking about stars, it's conventional to name the star after the constellation in which it appears and with a Greek letter in the order of its rank of luminosity within that constellation. So you might have Cassiopeia Alpha, Cassiopeia Beta, Cassiopeia Gamma, etc. But for radio sources, the convention is to use a Roman letter. So instead, you speak of Cassiopeia A, Cassiopeia B, Cassiopeia C. So Reber built this parabolic dish antenna. It's about 30 feet in diameter, and the focal point is about 27 feet from the surface of the dish. This is kind of like the prototype for a great many later radio telescopes. The parabolic dish is particularly useful because it can be used in combination or to detect a wide range of frequencies by changing out the antenna that you place at the feed of the antenna, at the focus of the antenna, and but the dish itself doesn't need to be changed out for different frequency ranges. The Dutch astronomer Jan Oort learned of Grote Reber's discoveries in radio astronomy and realized that a radio spectral line, that is one of those very narrow emissions that I spoke of earlier, such as the H2 regions, and that such a radio spectral line would be an important tool for discovering the structure of the Milky Way Galaxy. Oort had spent many years studying the rotation and structure of the galaxy using optical means. He was frustrated by the extensive clouds of dust lying in the galactic plane, which blocked visible light. and he appreciated that radio waves penetrate dust. Wirt assigned one of his students, Hendrik van der Holst, the task of figuring out what radio spectral lines might exist. And van der Holst predicted a superfine emission line of hydrogen in 1944. This is the H1 hydrogen I mentioned earlier, also called neutral hydrogen. Harold Ewen of Harvard observed the 21 centimeter hydrogen line in March 1951, and this year is the 70th anniversary of that discovery. Neutral hydrogen and carbon monoxide are important for mapping clouds of interstellar gas to determine their motion and density. After Ewen's observation, van der Holst, Wirt, and C.A. Mueller used a radio telescope to map out the Milky Way Galaxy, determine its spiral structure, and determine how fast it rotates. 21 centimeter hydrogen line observations continue to be important and are now vital in analyzing or observing conditions in the early universe. Here's a picture of Ewen's horn antenna. It's quite large. It's kind of in the shape of a truncated pyramid. This thing here, this apparatus, is a kind of folding cover that could be used to cover the opening of that horn antenna. I think he had some problems with snow falling in there and rain falling in there and then funneling down the horn into his laboratory and making a mess in the laboratory. A quasar is a quasi-stellar radio source. It can also be called a quasi-stellar object. These quasars were first identified in the 1950s as radio sources in radio sky survey maps. When observed in the visible wavelengths, they manifest as faint star-like points of light that have strange spectral lines that initially defied explanation. Doppler shift is associated with the apparent change of frequency as an emitter is approaching an observer with speed or is receding with speed. Think of the sound of a race car approaching versus receding. Wavefronts are closer together as the car approaches because each new wavefront is generated from a closer position, shortening the waves and increasing their frequency. The opposite happens when the car is receding. In an expanding universe, most objects outside our Milky Way Galaxy are receding from us with great speed, which results in a Doppler shift to a lower frequency and longer wavelength. This means that emitted light is shifted from shorter wavelengths, such as violet, blue, green, yellow, towards red, hence redshift. If instead the object is approaching us, the opposite shift can occur and it can be referred to as blue shift. These terms, redshift and blue shift, are used even when the frequencies are not in the visible spectrum, but are in the radio spectrum. In 1963, Martin Schmidt determined that the spectrum of a quasar he was studying was very highly redshifted, implying it is very, very distant. Given the quasar's luminosity and given its distance, that is, its apparent luminosity to an Earth observer, and its great distance, it had to be very bright and therefore very powerful, shining with the light of 2 trillion suns, hundreds of times the energy of our whole Milky Way galaxy. Quasars are believed to be, a typical quasar is thought to have a very compact region, only the size of our solar system, in the center of a galaxy in the early universe, billions of light years away, hence we are seeing them as they were billions of years ago. The compact region is an extremely active galactic nuclei that's powered by a supermassive black hole surrounded by a gaseous accretion disk that pulls in stars, consumes these stars. As the gas in the accretion disk is pulled into the black hole, it heats up greatly by friction and emits a great amount of energy. There's also synchrotron radiation going on because of intense magnetic fields associated with the black hole. The discovery of quasars bolstered the acceptance of the Big Bang theory. A typical quasar consumes 10 solar masses per year, about 6 Earth masses per minute. The brightest known quasars consume 1,000 solar masses per year, which is about 10 Earth masses per second. Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey, investigated 21 centimeter hydrogen with a very sensitive radio telescope. As they were tuning their new instrument, they found a 3.5 degree Kelvin radio signal evenly spread across the sky in 1964. This was the afterglow of the Big Bang, what we now call the cosmic microwave background, or CMB. This discovery, too, bolstered the acceptance of the Big Bang theory versus the rival steady-state theory. The cosmic microwave background is a black body radiation type of radiation. Later instruments, more precise instruments, determined the general temperature to be 2.7 degrees Kelvin. And other studies also revealed that there's an anisotropy or non-uniformity in the temperature of the cosmic microwave background. And these differences, this anisotropy, can be used to make inferences about the very early universe. Discovery and analysis of the cosmic microwave background has led to establishing, or estimating at any rate, the age of the universe at just less than 14 billion years. Here's the antenna of the instrument Penzias and Wilson were using. It's a pyramid horn antenna with this part being a segment of a parabolic surface which catches radiation and feeds it into the horn structure. That's a pretty big instrument. You can see the stairs here. You can kind of guess how big it must be. I wish I had something like that in my backyard to observe the 21 centimeter hydrogen line, but my wife won't let me do that. Pulsars were discovered by Jocelyn Bell in 1967 using the Interplanetary Scintillation Array at Muller Radio Astronomy Observatory near Cambridge, England. Pulsars are celestial objects that emit radio wave pulses that come and go at regular intervals, and this is caused by a rapidly rotating neutron star having a magnetic field that is non-aligned with the star's rotation. So here you see here you see a neutron star is rotating along this axis that has a magnetic axis like this, which is slightly misaligned. It generates synchrotron radiation. That's what these kind of blue cones here are. And if you're out at some point like this, as this rotates around, you're getting exposed to that radiation periodically on some periodic interval. That's basically how a pulsar operates. Neutron stars were predicted in 1933 by Walter Baade and Fritz Zwicky. They're thought to be the supernova of a star that leaves behind a superdense mass that comprises only neutrons. The mass of neutron stars range between 1.2 times the mass of the Sun and 2 times the mass of the Sun. They have a diameter that's about 12 miles, whereas the diameter of our Sun is 865,000 miles, so it's much compressed, very, very dense. And in fact, it's said that a sugar cube-sized chunk of neutron star would weigh about 1 billion tons, about the same as Mount Everest. Now, because rotational energy is conserved when the star compresses or crunches down, the rotation of a much smaller diameter neutron star is super fast. A pulsar in the In the heart of the Crab Nebula, the remnant of a nova has a period of 33 milliseconds, corresponding to a rotational speed of 1800 RPM. Another pulsar, discovered in 1982, has a period of 1.6 milliseconds, corresponding to a rotational speed of 38,500 RPM. Observations of pulsars can be used to deduce properties of the interstellar medium, the medium between stars, to study extreme states of matter, such as matter behaving relativistically, matter behaving as it does close to the speed of light. It can be used to search for exoplanets and to measure cosmic distances. Here's a picture of Jocelyn Bell next to the Interplanetary Scintillation Array. This was a phased array of 4,096 dipole antennas. It covered 4 acres originally and was later expanded to 9 acres in 1978. Well, Bell actually found the pulsars. The 1974 Nobel Prize in Physics was awarded not to her, but to her professor, Anthony Hewish. This led some wags to say that, well, this is natural, because after all, it is the Nobel Prize. So you might ask, what is interplanetary scintillation? Well, rays, radiation coming in from a distant source, a star, will dispose itself in planar waves coming into our solar system, but our solar system has a medium out there. It's got ions, other things out there, and the solar wind creates non-uniformities in that interplanetary media, which causes these planar waves to become disrupted, basically to scintillate, very much like a starlight will sometimes scintillate and twinkle in our own atmosphere. For the same reason, we have non-uniformities in the medium, the air, causes the light to slightly be perturbed. This is a picture of the European Space Agency Planck radio telescope, which was orbiting around the Earth, and it's a picture of the cosmic microwave background showing slight variations in temperature. Now, the cosmic microwave background is a snapshot of the oldest light in our universe, imprinted on the sky when the universe was just 380,000 years old after the Big Bang. It shows tiny temperature fluctuations that correspond to regions of slightly different densities, representing the seeds of all future structure, the stars and galaxies of today. A small portion of the cosmic microwave background is polarized. The polarization of the cosmic microwave background is the result of the last encounter of this light, radio waves actually, but light, with electrons, just before starting its cosmic journey to Earth. Thus, the polarization of the cosmic microwave background retains information about the distribution of matter in the early universe. This is a chart showing the expanding universe, the Big Bang here. The universe is expanding, and this is time. About 380,000 years after the Big Bang, hydrogen formed. It recombined and formed hydrogen atoms, but there weren't any stars. There were no light sources because it hadn't kind of condensed enough to form large masses, hydrogen, and start a star up with fusion into helium. And that didn't start until about 150 million years ago, from what I read somewhere else. I know that says something different there. This period here is called the Dark Ages because there were no stars, but yet there was neutral hydrogen, and we can observe that with the H1 21 centimeter hydrogen line. If we have radio telescopes studying that, we can see that. Here's a picture of the Planck radio telescope. And this shows the dual offset, just a second, dual offset Gregorian antenna with a first parabolic reflector here that reflects the incoming radiation, the second parabolic reflector here, which reflects it to a focal plane unit here, which is a series of frequency-tuned horn antennas that feed that signal to sensitive detectors. This is a picture of the focal plane unit. You can see the horns there, the different sizes correspond to different frequencies that they're tuned to. The radiometers in the focal plane units were artificially cooled with a complicated multi-stage cooling unit based on a pre-charged supply of liquid helium. When the liquid helium ran out, the instrument became much less precise, so it became useless more or less. Some of the detectors were bolometers, very sensitive detectors of electromagnetic radiation that were cooled down to 0.1 degrees Kelvin. So that kind of covers a high-level overview of radio astronomy and the history of radio astronomy. It's a relatively new discipline, born in 1933. It has produced many breakthroughs in cosmology. It blends radio technology, electromagnetic technology, and quantum physics. Now I'm going to talk about the neutral hydrogen H1 emission, which is what my radio telescope was built to observe. What it's looking for is an electronic spin flip transition, which is a very slim or small energy state change. Neutral hydrogen is said to be neutral because the electron is in the lowest orbit, but it's slightly energized because the electron is spinning in the same sense as the proton. It can spontaneously flip that spin to be the opposite sense from the proton, which is a lower energy state corresponding to an emission of a 21 centimeter wavelength at 1420 megahertz. And it does that with a randomness of about, and it has an 11 million year half-life. Hydrogen is very common in the universe. It constitutes 89% of interstellar matter, and most space is interstellar. Most of the space in the universe is between stars, so it's important. The 21 centimeter wavelength penetrates interstellar dust clouds, which are opaque to visible light. The magnitude of the 21 centimeter hydrogen line is a measure of the mass of the Milky Way Galaxy. And to the extent that it's shifted from its nominal 1420.4 megahertz, it's an indication of how fast the hydrogen that you're observing is moving relative to the Earth. That is, how fast is the hydrogen cloud or the arm of the Milky Way Galaxy that you're observing moving relative to Earth. So with a radio telescope, you're looking at sort of a myriad of different frequencies of radio emission. And these things combine together to form complex waves. Here I'm showing two waves, two emissions at different frequencies that when summed up create this complex waveform here. And that's just two of these. You can imagine it's much more complicated with just a whole myriad of these things. So what do? The Fourier transform is a mathematical transform that decomposes a function of time into a function depending on frequency. So if I do a Fourier transform of that wave here, I can represent it as an amplitude at the first frequency and an amplitude at the second frequency. So that's kind of how we might want to analyze this H1 hydrogen. See how much amplitude there is at that very specific frequency and make inferences based on that. So the question is, what can we see with a radio telescope? What can we see with this radio telescope? Well, we really can't see anything. Seeing is inherently related to optical vision with eyes. We use the term only analogously. My radio telescope, and probably many other radio telescopes, captures one datum at a time. It's analogous to capturing one pixel at a time. I can capture the amplitude of the H1 emission, which correlates with a mass of hydrogen in the antenna beam. I say correlate because the amplitude would also correlate with the distance of the hydrogen. So I can't map that amplitude directly to the mass in the antenna beam. I have to make some adjustments. And I also can determine the frequency shift by looking at where the peak of that radiation lies, and figure out what kind of a shift that is relative to the nominal 1420.4 megahertz. Here's a block diagram of my radio telescope. You see on the left upper portion, there's a cloud of hydrogen. It's emitting 21 centimeter radiation, which is picked up by the antenna. It's an analog signal, meaning it's varying continuously in both time and amplitude. It comes into a component that has three subcomponents: a first low noise amplifier, a surface acoustic wave bandpass filter, and a second low noise amplifier. It continues as an analog signal to a down converter, which downshifts that frequency from 1420.4 megahertz to something closer to 1.2 megahertz, and then it also digitizes it. It samples the analog signal at periodic intervals, changes those sampled values to a digitized value, and supplies a stream of digital values, time-sequenced digital values, to a computer that's executing high-definition software-defined radio software, which does a Fourier transform analysis and displays the amplitude of the radio signals at each of the frequencies within the band that we're looking at. And if we're lucky and we're seeing some 21 centimeter hydrogen, we'll see it being the peak above the background noise. So my antenna is a horn waveguide antenna. The horn was formed from aluminum roof flashing, cut to shape, taped together with aluminized tape. The waveguide is formed from an empty paint thinner can, and the antenna, the pickup, is a monopole antenna that is a quarter wavelength in size and is soldered to a connector. The dimensions of the horn itself, the waveguide, and the monopole antenna are sized to the 21 centimeter wavelength. They're related to that. Now, I mentioned that the analog signal leaving the horn antenna feeds a low noise amplifier. All amplifiers generate noise inherently. If it's a high level of noise, and you add that in with a weak signal, such as a 21 centimeter hydrogen signal, and then amplify that, what you get is mostly amplified noise. Well, that won't work. That's a problem. So instead, you need to use a specialized amplifier, which is a low noise amplifier. And then the noise is lower, with respect to or relative to the weak 21 centimeter signal. You add them up and amplify them, and the 21 centimeter signal is still significant enough that you can pull it out of there. I mentioned that we bandpass filter the signal. We've got all these frequencies that we're receiving. What we're interested in is these three things here, which are in the frequency range of our 21 centimeter. We bandpass filter it, which will keep these components at their full strength, but attenuate these other frequency amplitudes that are outside of that pass band on the shoulders of this curve. We do that with an electronic component. And then we down convert this. We shift it from 1420 megahertz down to about 1.2 megahertz. Again, with electronics, with a receiver. And then, as I say, we process it with high-definition software-defined radio-free software executing on a laptop to perform visual Fourier transforms. And then, if we're lucky, we see this. This is the noise. This is just background out there. But then there's this peak at a certain frequency that we hope is the 21 centimeter hydrogen that we're trying to observe. I'm not really sure if I've observed the 21 centimeter hydrogen line yet or not. There have been a lot of false starts that I've made. Just Tuesday, I was out observing, and in a field in Skiatook, my backyard has trees and a back porch roof that I fear may be interfering with the beam of my antenna, feeding in hot temperature, black body radiation at 290 degrees Kelvin. I want a wide open sky without anything kind of beetling over my antenna beam. So I went out to this 5-acre field and collected some data. I'm getting the frequency of a peak. I'm getting the amplitude of the peak here. And this is the noise floor. I spoke about the noise floor earlier. So these are in decibels, and they're negative values. So a smaller negative value is higher amplitude. This is a graphical representation of that. These short lines here are my noise floor, the noise that I measure at each one of these 15-minute intervals. And the long lines are the peak of the amplitude that I'm seeing. And it's increasing over time, which I would expect if the Earth is rotating on its axis and bringing the hydrogen cloud into the beam of my antenna. What I would then expect is, as the Earth continues to rotate, that hydrogen cloud would rotate out of the beam of my antenna and the amplitude would go down. Unfortunately, my laptop battery expired at this point, so I couldn't continue my observation. I now have a 12-volt DC to 120-volt AC converter, so I can keep my laptop charged while I'm out in the field doing more of these observations. So when I started out, my observation goals were to just to observe the 21 centimeter hydrogen line, period. And then I wanted to further see a variation in the amplitude at different places across the Milky Way Galaxy. I wanted to detect Doppler shift at different areas in the Milky Way Galaxy, meaning hydrogen clouds are moving faster towards me or slower towards me or faster away from me. And finally, complete a drift scan to observe the plane and center of the Milky Way Galaxy, where I would let the instrument run for 24 hours at a time, direct it to one elevation, and then change the elevation and observe again for another 24 hours, letting the Earth kind of revolve the field through different right ascension values. It's possible I've achieved the first 3 of those objectives, observation goals, but probably won't be the last one. That's a pretty aggressive goal. My project goals were to learn about radio telescopes generally, learn how to use the signal processing software that I have, learn about astronomy from a hands-on approach, and develop an appreciation for historical findings produced from the 21 centimeter radio work historically, and also maybe to inspire myself to undertake additional radio astronomy projects in the future. And I think I've probably accomplished most of those things. It remains to be seen whether I pick up another project. The inspiration for me to start this project was reading an article in October IEEE Spectrum magazine titled Build Your Own Radio Telescope by David Schneider. I exchanged some emails with Mr. Schneider, and he graciously provided some helpful clarifications to me. I'm Michael Hann. I've been an on-again, off-again astronomer since I was 12 years old. This is my Christmas present when I was young. I like to watch meteor showers, binocular observations, and some radio astronomy projects like this H1 hydrogen project. So that concludes my presentation. Are there any questions? I'd also point out that this is my horn antenna sitting on this table up here, and my two components, the low noise amplifier, bandpass filter, and the down converter digitizer is sitting on the table. They're just small electronic components. Are there any questions? Those two electronic components I purchased. They were actually described in that article I mentioned, and they're available from a commercial source. And they're particularly, at least the amplifier component is to the 21 centimeter lines. It's literally aimed at that. The other one is just a software-defined radio, which could be used for picking up FM radio stations and other things related to software-defined radio. Okay. Well, there is hydrogen emission coming from other sources outside the Milky Way Galaxy, the Andromeda Galaxy, other places, and such and so forth. But it's going to be much weaker than it is coming from the Milky Way. So my instrument almost certainly couldn't pick them up. It's a touch and go situation whether it's picking it up from the Milky Way Galaxy. I haven't concluded that fully yet, but unlikely to be able to pick it up from a more distant source. Other more sensitive instruments definitely can pick up that from other places. I mentioned earlier the importance of H1 21 centimeter astronomy for observing the early universe, and that's what some of these other instruments are doing. They're looking at stuff that's very highly redshifted, well outside the Milky Way Galaxy, to do their analysis. So yes, you can do that, but not my instrument. Yes?
Do you have any intention to scan and basically create an image of an area of the sky?
Do I have that intention? Yeah, that was, I mentioned earlier, I was kind of interested in doing what I call a sky survey or a drift scan. I think I called it a drift scan. That's what I was talking about. And I initially wanted to do that, but it would be a big challenge. And particularly, it might be a challenge. And I think I basically was unable to observe the H1 21 centimeter hydrogen until recently. And what I've done recently that's different is I've gone to a different site. It's out in the country, away from possible interferers, free of black body radiation from over looming trees. But also I've identified a particular place in the Milky Way Galaxy at 80 degrees galactic longitude, which is supposed to have a concentration of hydrogen. So I'm looking at that, and I think I'm seeing that. But if I get outside of an intense concentration, I'm guessing that the low sensitivity of my telescope will just prevent me from seeing anything. So what that means is if I did a drift scan, the scan that you're talking about, most of it would just be no signal until I hit one of those intense peak areas, and then I would be able to pick something up. Now, a better instrument, there are ways of improving an instrument like this. Build an antenna with more gain, get a low noise amplifier that's lower noise. My amplifier has a noise figure of 1.05 officially, dB. Others are available at 0.3 dB noise figure, which is considerably better. I don't know how much difference that would make in terms of the sensitivity of my instrument, but those are possible ways to approach that and improve on what I've got. But without something like that, I just don't think this telescope would be sensitive enough to accomplish anything by that kind of a scan. That would be an interesting thing to do, but this isn't the tool to do it with. John?
Parabolic like Reber and
Well, I'm not exactly sure what you mean. Antennas tend to work much the same, and the things that are important is what is their bandwidth, what's their frequency bandwidth, what's their frequency response. Parabolic dish is very broadband, depending on what you put at the focus. You're going to have something to pick up the reflected radio waves at the focus, and that will be frequency sensitive, frequency tuned. But another important parameter of antenna behavior is its aperture. And it's not really a different concept from the diameter of an optical telescope. Bigger is better. You capture more, you get more angular resolution. And so a bigger horn antenna would get you more of that gain, more precision, and it would make it more sensitive. And likewise, a bigger parabolic dish works the same way. Does that answer your question? Yeah. I mean, I built this because this is what was described in the article, and it was said that it was something that would work to accomplish that. So I think maybe I would like later to do some work with parabolic dishes because they're available. You can kind of find those disused maybe in people's garages that are the old TV dishes that are kind of big. Those are very useful for this kind of a project. If you're willing to do some kind of custom work to get the feeds set up the way you want them to, and make other arrangements to make them work for radio astronomy versus television. Any other questions? Thank you.
Thank you, Michael. That was quite interesting. If you're out there and interested in that, you can look up on the internet. It's called Itty Bitty Radio Telescope. It's a high school project that you can take an old, like you said, an old dish network antenna, and it shows you how to make a little receiver and things, and you can pick up things like that. There's also, Jupiter gives off radio signals, and they use I think it's a dipole type thing, it's a string of wires to pick up Jupiter when it's coming by. So there's a lot of ways to do different kinds of astronomy like that, so that's good. Afterwards, some people like to go out to, down the street, there's a Louis Grill and Bar, and just kind of sit around and visit and such. So you're welcome to do that if you like, or just to visit with other people and see what's going on. So our new people, I hope you'll come back. Be sure that I get your email, and if you're not on our guest email list, you can start getting our newsletter and other things that's coming out. Or you can go to the website. There's a little tab there that says About, and look under there. You can see this past month's newsletter. Plus, there's, I don't know, Rich, it goes back to about 20 years, doesn't it? our newsletters are on there, so you can go back and find out those things. But if you kind of all move over this way, I can get Dan to turn up the lights. I'm gonna try to take a picture of the audience. Right, so everybody kind of move
Light's
here so I
already
can
back.
get it shot that way, and maybe Dan can turn up a supernova on the screen. And
You're at max level, my man.
that's it, huh?
You're in a planetarium. It doesn't get much brighter.
Okay. You can shut down the Zoom if you like.
Okay.